Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Steve Howell with us today. Hello, Steve.
Hey Frank, how are you today? And happy listeners.
Yeah, it is August 11th, 2025 as we record this. And let's see, I'm doing very well. Phoenix is, of course, in its full summer bloom here. We'll probably hit 41, 42 C today. So, border 110 or so for those who are in the Fahrenheit system. And we haven't gotten any of the traditional monsoons we get out here yet, but we will soon. So it's the rainy season in Phoenix. And Steve, what is your geolocation?
So I live near San Francisco, and unlike California, we've had an exceptionally cool summer for us. And that
Okay.
means that our temperatures have hardly even reached 80 degrees Fahrenheit. So for us, that's pretty cool, which is kind of nice, except my tomatoes and pepper plants in my garden are not so happy.
Kind of reminds me of a Mark Twain quote somewhere in there about the coldest winter I ever spent was a summer in San Francisco.
Yeah, San Francisco's been in the 60s many days. Yeah.
Oh, gosh. Well, we'll have to wait for October, so which is usually when California gets some really nice weather. So
Yeah, absolutely.
there we go. And Steve, what do you like to do for research?
For research, I like to think about problems that need a solution and then think of clever ways to figure them out. I've worked on many things in my career, a lot of instruments to kind of go do fun, fancy new stuff
Yeah.
on binary stars, on active galaxies, and on companions to very bright stars.
Which is gonna bring us to this very awesome article here. And let's see, where is my share button? Here we go. And this is an APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The Probable direct imaging detection of the stellar companion to Betelgeuse. And Steve, take us away.
Yeah, what a great title, huh? That Probable has really been fun. So before we get into the paper, let's talk about the co-authors because no one does this research alone here. So my
Absolutely.
co-authors, David Ciardi, Catherine Clark, and then I'll skip over to Elise Furlan because they're all from the Exoplanet Archive at Caltech and IPAC.
Mm-hmm.
Uh, Doug Hope, we'll talk about him a little later too when we get to the final part of this. So Doug Hope's a great collaborator in terms of software and great techniques for speckle imaging, and Colin Littlefield, primary observer and data reducer. So very cool. And
Great
and
show. Great
yeah,
show.
all those folks are important, of course, to all put together this puzzle.
Very nice. Okay, let's go.
Yeah, so Betelgeuse is a fantastic star. We all love it. And I think that to start off this paper, we should recognize that two papers came out in the fall of 2024, early 2025
Yes.
on Betelgeuse.
Yes.
They were papers by Gerard Goldberg at the Flatiron Institute and a paper by Morgan McLeod at CFA.
He
And to
a
me,
buddy for Beetlejuice, I do recall.
yeah, that's right, for Beetle Buddy. Yeah, that was one of them. And so the interesting part of those papers is they were independently done by a fairly large team in each case, and they reviewed over 100 years of radial velocity data, astrometric data, photometric data, multicolored data, all kinds of spectroscopy,
Cool.
tons and tons of data, and went through in great detail what causes all these issues and things we've seen with Betelgeuse for over 100 years.
Right.
And they both concluded pretty much the same thing, that this extra long period, which we'll get to in a moment, has to be due to a stellar companion.
Okay.
So Betelgeuse has been known for a long time to have roughly a 200-day period. Is that
Hmm.
right? No, sorry, 400-day period, which is Betelgeuse's pulsation period.
Right.
And if you look at figure one, you can see that quite well. You can see the pulsation period
Mhm.
to the left of what we'll call the great dimming, and we'll talk about that in a moment. And
Okay.
you can see that period. But what you also see here is there's sort of part of a sine curve there that you can see starting from, say, the year 2020 to the end of the plot at 2025. If you look at the V data, these are all data from the AAVSO, you can see there's another part of a sine curve there. And
Hmm.
that is this period that's about 2,000 days long,
Okay.
so something like 6 years. And that period has been sort of stumping astronomers for a long time. It's too long to be a pulsation period. Betelgeuse isn't a big enough star, even though it's quite large, but it's too long to be a pulsation. And so both of these papers I mentioned concluded it must be a companion.
Okay.
And they not only concluded it must be a companion, they made predictions about the companion.
Oh, good theorist. Good theorist.
Right. They made predictions of its orbit. They made predictions of when it would be at elongation, that is the widest separation from Betelgeuse.
Yes.
They made predictions of its likely mass. And those were the things that got me interested and got my co-authors interested in thinking maybe we should go look for this companion.
Cool.
And we decided to try a technique that we've been doing for many years for many other projects called specointerferometry. And the big advantage of that is you can actually look directly at Betelgeuse. This is difficult for lots of people to do because Betelgeuse is very bright.
Yeah.
And so you can't, in most telescopes with most instruments, look directly at Betelgeuse. It's just too bright. It saturates your instrument. It saturates your camera.
Yes.
And so other people that tried to find this companion after these papers came out, these two teams decided to look. They tried the Hubble Space Telescope, which of course could not look directly at Betelgeuse, had to try to do spectroscopy of sort of the scattered light. And they tried with Chandra looking for X-ray emission to see if the companion, as it plowed through material around Betelgeuse, would make X-rays. Maybe it was a neutron star. And neither of those studies were successful at finding anything. It was a great attempt, but nobody can look at Betelgeuse. So the two things you need to find this companion, one was, can I look directly at Betelgeuse? And two is, can I get the resolution to separate Betelgeuse from the companion at 52 milliarcseconds away? Well, at the Gemini 8-meter telescope, we had an instrument that we believed could do both of those things. We observed it in early December, which just magically turned out to be, when these papers came out in the fall, was the perfect time to look at it when the companion would have its greatest separation from Betelgeuse itself. And that separation, by the way, 52 milliarcseconds, in terms of how far that actually is from the star Betelgeuse, the companion orbits in the chromosphere of Betelgeuse. Yes. So it actually plows through material as it orbits. And in fact, the photometric variation that makes this 2,000-day period is likely this star ionizing a little extra ionization in the chromosphere of Betelgeuse as it orbits around. And that little extra brightness is seen as this long-term photometric period. It's called a long secondary period, an LSP.
Nice. LSPs. Okay.
LSP, yeah. So anyway, we observed the star, we reduced our data, and sure enough, there popped out the companion exactly where it was predicted to be, exactly at the separation, and roughly the same delta magnitude and then inferred mass.
Cool.
And in this paper, the reason we put probable in the title was because our detection was only a 1.5 sigma detection.
Yes.
So kind of the gold standard in specointerferometry is 5 sigma.
Right.
The gold standard kind of, in just science in general was at least 3 sigma, right? So how do we believe a 1.5 sigma detection, right? Well, there's a number of things. One is the companion was exactly where it was predicted to be, in separation and in position angle.
Yes.
The second thing is the inferred delta magnitude, that is how much fainter it was than Betelgeuse itself, was about 6 magnitudes. 6 magnitudes was roughly what the predicted value would be.
Cool.
The other one was that the inferred mass, and we'll get back to this because this is a tricky thing, the inferred mass was roughly in the range that the theoretical models from radio velocities predicted that would be the mass range.
Nice.
We also made an observation in February of 2020. And if you go, I think it's to figure 2. We'll come back to this figure here in a minute. I think it's figure 3, I mean.
Figure 2.
We made an observation in February 2020 during what was the so-called Great Dimming. This event was when there was a large mass ejection from Betelgeuse, and that blocked some of the light from Betelgeuse. So Betelgeuse faded. And a lot of people thought that fading meant that Betelgeuse was going to be a supernova.
Oh, boom. Yep.
Yeah, I was there too, man. I would love to see Betelgeuse blow up. But anyway,
So,
it turns out Betelgeuse, the reason we looked at it then was to see if Betelgeuse actually was expanding to get fainter, then we should be able to measure its size, because we can resolve Betelgeuse and see that its size would be bigger. And our image here on the left shows Betelgeuse in 2020 during the Great Dimming.
Yep.
And it's no bigger than it's ever been, roughly about 40 milliarc seconds in diameter.
Mm-hmm.
The image on the right here is our image in December of 2024, and you can now see there's something different about it. There's the little smudge of the companion that the arrow is pointing to. In February 2020, the model predictions were that the companion star would be in front of or behind Betelgeuse. You would not be able to see it. And in fact, we did not see it at that time. So seemed pretty exciting. And even though it's only a 1.5 sigma, and the reason is this is an incredible delta magnitude, 6 magnitudes fainter at 52 milliarc seconds. That's this pretty cool observation that we made here. And I should point out, if people notice this figure, there are actually 2 images.
I was going to go there. Yes,
everybody goes there.
Right here.
So if you know about interferometry, you know that you always get, in Fourier analysis, you get a 180-degree ambiguity. It could be this one, it could be that one. So before, and I emphasize this, before I looked in detail as to where the companion should be, you do some other work in your software that allows you to look at the phase of the information, and your software can make a decision based on statistics which one of these ghosts is the real object. And we've done tests with much brighter stars of looking at, when we see the ghost, which is the real object, which is the fake object. And in something like 99.8% of the time, we always get the right answer.
Cool. Good.
So I had predicted that the thing the arrow points to would be the real companion. And in fact, when we then looked at these papers I mentioned before, that's exactly where it was predicted to be.
Nice.
So pretty exciting. And just for reference, you can see in the top right panel of the right image there, that's the size of a typical single star that you would measure with Gemini. And it's basically the diffraction limit of the 8-meter telescope. So that object is not resolved. But you can see Betelgeuse is quite large. Right? It's pretty easy to resolve Betelgeuse with an 8-meter telescope.
Nice. Very good. That's impressive.
So that was the beginning of thinking this is the companion. So we did some other things. We took our data set, we divided it into 3 parts, and we reduced each part independently. Each independent part found the same companion at the same place, and it was always that companion that was pointed to as the correct companion. So that gave us some faith that it was the right companion as well. The other thing we wanted to check was, could this be a background star? Because of course, Betelgeuse moves, and there could be a star in the background that just happens to be in the line of sight of Betelgeuse. And so I think the next figure, well, 2 more. Sorry, I'm skipping around here a bit.
It's all good. It's all good. Figure 5. There we go. Stretched.
Sorry, keep going. 1 more.
Figure 6. Not stretched yet.
Yeah. We'll get back to there.
We're still compact. Here we go.
That's right. There you go. Right. So what we did is we looked at the motion of Betelgeuse over time. And if this star were a background object, then we would have seen it in our field of view in the February observation as well. Because our field of view covers roughly the size of this plot. So we would have seen it a little further away from Betelgeuse, but we would have detected it in February 2020, and we didn't. So therefore, we've eliminated that it's a background star. It actually is a companion to Betelgeuse. So that was pretty interesting as well, because there are background stars, and if you're looking 6 magnitudes fainter than a star, your chances of seeing a background object are increased.
Very good.
Right. Yeah. So you can go up to a figure above this.
Sure. Stretch.
Yeah. We'll move around here a bit.
All good.
Figure 4. Figure 4, please.
Figure 4. You got it. Okay. 2 wavelengths. 2.
Yeah. There you go. Right. So in figure 4, what we did here was we put what are called contrast curves. So this blue curve and this red curve are the magnitude contrasts that we reached as a function of angular separation And you can see that they just get down there to 6 magnitudes and then go pretty flat out toward 8 magnitudes by the time you get near an arc second. And
Right.
the object there with a fairly large error bar, I mean, it's a magnitude error bar, right,
Yep.
is the companion we detected.
Okay.
And that error bar is not unusual for something at this basic level of a detection. And
Okay.
of course, what that's going to mean is that any parameters we derive for this companion are going to have big error bars as well. They're going to have some uncertainty in them, right?
Hence the title.
That's right. Hence the title. That's right. But I think all these other points sort of, they could all be a coincidence, but I think it's pretty unlikely. And again, we'll talk a little bit in the future stuff about some other work.
Nice.
So this particular object, if you go now one more figure, we'll actually
Okay.
stop on the next figure.
That will stretch.
So what we did in this figure is we really stretched the image in like super log, min max stretch. And the reason we did this is we wanted to try to measure astrometrically the position of the companion,
Okay.
to try to get as accurate of a position as we could get. The magnitude, as we saw in the previous plot, is pretty uncertain, right? We acknowledge that it's pretty uncertain, and there's some interesting reasons why it might be uncertain. But here we wanted to make sure we knew the astrometry. So you can measure the center of Betelgeuse, the center of the big red thing in the middle, and you can measure that one pixel that has the brightest light from the companion. And that gives us a very good measurement of the astrometry. And just to point out the scale bar here, which to me is just so amazingly phenomenal, right? That scale bar is 0.1 arc seconds.
Yes.
I mean, this is just pretty cool stuff that you can do. And I encourage all of you to write proposals to use this instrument. It's open to everybody to use at Gemini.
Awesome.
So have a ball
Tack,
with
I
it.
hope you're paying attention, Tack. I think this is also irrefutable evidence that stars are square.
It is indeed. And we could talk about a whole paper I wrote years ago on actually making stars square to do high precision photometry.
Very cool. Very nice.
That was pretty fun too. All right, so let's talk a little bit about what the companion might be.
Okay.
Okay, so the companion, if you notice before, and even here in the stretched image, you can see that the companion is not just one pixel. So
Yeah.
to give you a scale here, and you can read the paper, but here to give you a scale, each pixel here is 0.01 arc seconds in size. And so the companion is not completely defined as one pixel here. It's kind of fuzzy. And part of that could be that, as I mentioned earlier, the companion star, whatever it is orbiting in the chromosphere of Betelgeuse.
Yes.
And so it could be that what you're seeing is not just the light from the companion star, but you could be seeing some scattered light or some ionization light from this sort of blob that moves around as it ionizes the chromosphere as it orbits Betelgeuse. So that also means that not only the magnitude uncertainty of it, but what the star actually is, we may not be detecting directly just the companion star, right?
Yes.
We also only have one filter measurement here.
Okay.
We have a delta magnitude in one filter.
Yes.
And so with one color, basically, you can't say much about the SED, right?
Yes.
The prediction, however, was that this object would have a mass between about 0.5 solar masses and 1 or 2 solar masses.
Okay.
Betelgeuse itself is 16 or 18 solar masses. So by comparison, this star is pretty wimpy. Betelgeuse is a pretty young star as things go in astronomy, 10 million years old, right? A mere tad of a star. And so what that means is that this object at something like 1 solar mass hasn't even made it to the main sequence yet.
Yes.
So what a fantastic pair of stars. You have a star that's already evolved to become a red supergiant and another star that hasn't even quite made it to the main sequence, orbiting each other. And it's not going to be a great ending for either of the stars.
Well, it might be pretty great depending on what your interests are there.
Well, that's true. Yeah, for us, it'll be cool to see it blow up. But the star in the chromosphere, because it's in the material, has orbital drag. And so it is spiraling in.
Yes.
And the prediction is in about 10,000 years, it will basically be engulfed in Betelgeuse itself. Of course, in that time, Betelgeuse may blow up as a supernova. We don't know. So it's kind of a fun binary pair. They, of course, form together. Betelgeuse being more massive evolved so much quicker. So if we look
Mm-hmm.
at figure 7, which I think
Okay.
is now maybe next, I might be in order now. Look at me go.
No,
Ah,
six,
no, one more, please.
seven. Your order is hopelessly lost. We're good.
Yeah, that's right. Yeah. All right. So this is an
Ah,
isochrone at 10
yes.
million years.
Yes.
So it shows the effective temperature and the sort of B magnitude. So our measurement was in a filter that was essentially the center of the Johnson B magnitude system.
Okay. Okay.
And you can see Betelgeuse, the red dot there at about 3,000 degrees or so, and it's evolved. And the blue rectangle with fairly large error bars is the companion, or at
Mm-hmm.
least the thing we see that's at the location of the companion, whether it's star photosphere or whether it's star photosphere plus some
Yes.
ionization material and
Mm-hmm.
fuzzy material around it in the chromosphere. And so if you take this B magnitude, and again, it's one magnitude, but if you take that magnitude and the delta magnitude from Betelgeuse, you
Yes.
can assign this object a
Six.
mass, and the
Okay.
mass is about 1.5 solar masses.
Wow. Cool.
Okay. Now, again, there's error bars on that. You can see how big that blue rectangle is there. So, I take that
Mm-hmm.
with a grain of salt or a ton of salt and
Mm-hmm.
something. So, we need to study the object further, of course. And we now
Absolutely.
know it's there, so we now know we can study it. Unfortunately, with a 6-year period, we now have to wait almost 3 years to get the object on the other side of the
Correct.
star.
Right.
And so, but by that time, we'll all be prepared. We'll be prepared
Yes.
to go at this with new instrumentation, with all kinds of things to do and study it. So
Mm.
that'll be pretty cool. So
That's
there's the
great.
story. That's the story of the companion of Betelgeuse. It took tons of people, tons of years to put all this data together. It took these 2 large studies to really conclude it must be a companion. It took a clever instrument and a clever observation to find it, and that's pretty fun stuff.
I would like to compliment the cleverness of the observers doing this. So very
Thank you,
nice.
Frank.
Very nice.
Thanks.
Beautiful, beautiful. Beautiful work, Steve, and beautiful shout out to your colleagues for helping with this. Very awesome.
Oh yeah, it's a fun group, and we have a saying that in our research groups and our collaborators there can be no jerks, and so everybody has to be fun or they don't get in the group.
Very good. Yes. So let me ask you, kind of touched on it. And we're sort of an impatient lot, and waiting another 6 years or 3 years for something to come around where you want to answer now. So let me ask it this way, where do you think we go from here over the next couple of years on this topic? Are there other wave bands that one might want to consider? Are there other observations maybe on discretionary time that one could take a look at? And so where do you think we go from here in the short term over the next couple of years?
Yeah, well, of course, that's a great question. We all want to know as well. And 3 years, in astronomy is like the blink of the eye, but I don't want to wait 3 years either.
Right.
So here's a couple things we're doing. So right now we're finishing up another work on this same data set
Okay.
where we're reducing it by a very different kind of method. So this data set was reduced using pretty much the way most people reduce speckle interferometry with Fourier analysis.
Yes.
But there's also another reduction technique that we've been working on for maybe the last 4 or 5 years. That's called multi-frame blind deconvolution, and that sounds like a fancy name, but it's basically the technique that is used a lot by the VLBI and radio observers. If you remember their image of a black hole that was presented.
Yeah, yeah.
It's a technique where you spend a lot of CPU time, which is easy to do these days,
Mm-hmm.
and you do modeling of every speckle frame and go look at trying to fit the best thing that models your speckle frame. Anyway, so if people care, there's a paper we wrote last year about this technique, but we've been applying that technique to this data set, and I think we'll all soon see some very positive results from it. And what it's going to tell us, much better than we know now, I believe, is a far better delta magnitude.
Okay.
So speckle interferometry is really great with astrometric information, but it's really not so perfect. It's good, but it's not so perfect with the delta magnitude information.
Mm-hmm.
So for a good signal to noise image in speckle interferometry, we can know the delta magnitude to about plus or minus 0.2.
Ooh, nice. That'll cut down that error bar on that then.
That's right. That's when you get a 5 sigma detection, right?
Right.
Or higher.
Right. Mhm.
In this case, as we saw, we know the delta magnitude to plus or minus one-ish
Right.
or something like that, right? So I think we'll get a better delta magnitude, and that will let us constrain more of things like the mass of
Yes.
whatever we're seeing, right?
Yes.
And color of it. The other thing that we want to do in the future is I mentioned this long secondary period, this thing called LSP.
Mhm.
So many red supergiants, and if you look up in the night sky and you see a red star, chances are it's a red supergiant, show these long secondary periods.
Uh-huh.
Antares A, for example, is the prime thing. There was a paper in 2013 by Pugh and Gray,
Okay.
which looked at kind of the same idea as these Betelgeuse papers and said, we believe there's a companion with a 6-year period that orbits Antares A.
Curious.
It's a little closer in separation, so it's going to be a little more challenging for us, but we're going to go look and see if we can find that companion
Oh,
as well.
very nice. Very nice.
So
Yeah,
that'll
yeah.
be fun. Anyway, so there's many red supergiants, and it doesn't really surprise you once you think about it, because a red supergiant used to be a massive B star or a massive O star.
Yes.
And we know that massive stars are many percents of them are binaries,
Yes.
right? And so it's not surprising that red supergiants, which used to be a massive star, have a companion. The
Okay.
question is, can we find them and prove that?
Nice.
So that's the next adventure. It turns out Antares, much like Betelgeuse, with a 6-year period to its companion, you must wait until it's at elongation to try to see it.
Yes.
The next elongation for Betelgeuse is the fall of 2027.
Mhm.
The next elongation for Antares is July 2027.
Okay. So it's a twofer. It's a twofer.
Isn't that hilarious? So my prediction is all red supergiants have companions with 6-year periods, and they already elongation in 2027.
There's some cosmic harmony in that,
That's right.
somewhere. That's a very bold prediction, Steve. All of them
Yeah,
have
it is.
your periods, but I like it. Put your predictions out there. It's great.
Yeah,
Awesome.
it's fun.
Very cool. Very cool. Well, it'll be really exciting to see this field develop over the next couple of years. People have been looking at Betelgeuse and Antares for centuries, so it's always cool to find something new in what is an old friend. So
It is, absolutely. And, I've always loved Betelgeuse. And now if I go outside at night in the winter and I look up and I see it, I'll never see the companion with my eye, but I'll know it's there.
absolutely. Very cool. Very cool. Steve, I want to thank you and your team so much for walking us through your very awesome article.
Great. Thanks, Frank. And so great. The IOP and AAS were fabulous in helping me get the paper published correctly. And so thanks a lot for that.
Yay, Fred. Yay, APJ loaders. All right, that'll do, everyone. And I hope this made your red supergiant Betelgeuse days just a little bit better. And we will see you on the next one. Bye-bye.
Bye.